going to go through the differentiation of this function in two different ways. First up, actually, this is the best way, but it's a bit more obscure because it's typically not covered at A level. And it's to do something called logarithmic differentiation. Before we differentiate, we actually take logs of both sides. So ln of f of x equals ln of x to the power of x squared. Now we can bring the x squared down. So that's why this works really well. And then I'm going to use implicit differentiation, differentiate each side. So I've got ln of the function. So when I differentiate it, I differentiate the outside to get 1 over f of x. And I times by the derivative of the inside, which is f dash x. So we still get the f dash x, it's just we get the f of x as well. And now can you apply the product rule to this function? So I've got u and v. U dash is 2x, v dash is 1 over x. So u times v dash will be x squared times 1 over x. And then v times u dash will be 2x times ln x. This simplifies to x plus 2x ln x. And therefore f dash x, I just times through by my f of x, which I can now put back in. So I'm going to have x plus 2x ln x times x to the power of x squared. Really nice approach, and if you've never seen it before, then look up some more examples of it, try it out. It is really useful, especially when you're dealing with exponentials. Imagine if this function was even more complicated. It just really comes into its own. Method 2 is to use a similar sort of approach to how you learn how to differentiate 2 to the x. So we can write x, let me just write f of x equals x to the x squared. Right, now what I want to do is write it as e to the power of something. So when we have 2 to the x, we write it as e to the ln 2 to the x, which becomes e to the x ln 2. That's how we know that when you differentiate 2 to the x, it's ln 2 times 2 to the x, because you can use the chain rule on this part here. So a similar way, it's going to be e to the ln of x to the x squared. So similar properties are now being used. I'm going to get e to the, bring the x squared down, e to the x squared ln x. And that means f dash x, right, now I need to use the chain rule. So I'm going to use the outside-inside version of it. So differentiate the outside first. It's just e. E stays as it is. In fact, that's the original function. And then I times by the derivative of the inside, which actually I worked out before. It's just this thing here. So I can bring that in, and I get the exact same answer. So I'm going to get x plus 2x ln x. I just feel like this one is a little bit easier to implement once you've got your head around it. And yeah, you don't have to think about using the chain rule. And it's a bit more general, like I said, for when the functions in the exponent get even more complicated. In any case, this is our answer for f dash x. So remember, we're being asked to find the x-coordinate at the stationary point, so we can set this f dash x equal to 0. And that means x plus 2x ln x times x to the x squared is equal to 0. But this thing is always going to be greater than 0, just like an exponential is always greater than 0. Remember, we're also told that x is greater than 0. Actually, that's important because if x was negative, then it'd be a slightly different scenario. But we can just quote that here, and that means we can divide through by it, leaving us x plus 2x ln x equal to 0. We're going to factorize out the x. So x times 1 plus 2 ln x equals 0. And normally I'd get a solution x equals 0, but two things. First of all, we're told that x is greater than 0. And secondly, ln of 0 is not defined. So actually that wouldn't have been we would have rejected it anyway. So I can just cancel it out, and I'm left with 2 ln x equals minus 1. Ln x equals minus a half, and therefore x is equal to e to the minus a half. That's actually how I left it, and it's absolutely fine. You could write it as 1 over e to the half, and therefore 1 over the square root of e. That's potentially like slightly neater, but both are absolutely fine.